let's have a look at phase diagrams of materials. To understand a phase diagram, let's simply draw one and then annotate it so that we have everything, so that we can understand sort of where everything comes from. A phase diagram looks like this. We have pressure on one side and temperature on the other axis. So pressure is going up as we go from here, and temperature is going up as we go that direction. What a phase diagram is it's this. It tells you what the phase is at a particular pressure and temperature for a given substance. We'll just draw a sort of a generic phase diagram so you can get you can sort of see what the various points and lines might be. But so, for example, I'll put in some points. So let's say we have something like this. I'll call that point A, that point D, this point B, and that point C. Within this region, at relatively low pressures and high temperatures, you can imagine a material would be a gas. At relatively low pressures and low temperatures, you might imagine that something is a solid. And then this region is a liquid. So anytime you have a temperature and pressure combination that falls within this region here, that material would be a solid. Anytime you have a pressure and temperature combination that falls within this region here, that material would be a gas. Anytime you have a pressure and temperature combination that falls within this region, that material would be a liquid. Let's look at some of these. So it's relatively straightforward to read a phase diagram. Oftentimes you might be quite simply interested in, if I am at a certain temperature and a certain temperature and a given pressure, what would be the phase of the material that it would exist under? Oh, and in this case, okay, maybe say it's a gas or something. So that's one way to use a phase diagram. So let's look at some of these others. So let's look at this line AB. Let's look at this line AB. So this line here. This is the line between solid and liquid. This line here would indicate the change in freezing point or melting point, however you want to call it, right, with pressure. So what this tells us is that there is a pressure dependence on the melting point of a substance. In this particular substance, it's got this curve here. Let's look at this line here, AC. This is the curve which tells us what the vapor pressure is of a substance is. Let's look at line AD. This is the variation. So the variation in vapor pressure for sublimation, right? Because in this case, we're going from a solid directly to the gas. And this line is telling us what that vapor pressure would be, right? The pressure of the gas over that solid material, what it would be for sublimation. So there's going to be the variability of that between those two things too. There's one point. So AB, AD, AC, those are all functions, right? It's a function what the shape of that is going to be. Point A is a special point. It's called the triple point. And like its name implies, this point here, this point right there, is a point at which, if you were at this exact pressure and this exact temperature, you would have, or could have, all three of those materials present at the same time. All three phases are in equilibrium. And then finally, one other point I want to point out is C, this point here. That's something called the critical point. It's a temperature, above that point, it's a temperature and pressure above which the substance really no longer exists. Above this temperature and pressure, the substance really doesn't exist anymore. The energetics are such that it's not favorable for that thing to be a molecule, for example, or it's not favorable for it to have a cubic, or it's not favorable for it to have a crystalline, or it may not be favorable for that thing to exist anymore. It's just too hot. It decomposes, that material. So those are the points of a phase diagram, and let's look at a couple of different ones. We drew a sort of a generic phase diagram here. Let's look at a few different phase diagrams. Here's a phase diagram for water. At one atmosphere of pressure and 0 degrees Celsius, that's the melting point. So that's what we're seeing right here. That's the point at which the solid becomes a liquid. Or we can call it the freezing point, right? It goes the other direction from a liquid to a solid. At 0 degrees Celsius and 1 atmosphere of pressure. At 1 atmosphere of pressure, if we raise the temperature another 100 degrees, water starts to boil, right? It becomes a liquid. Or it becomes a gas, excuse me. The triple point is given right here for water. So if you were at 0.01 degrees Celsius and 0.006 atmospheres of pressure, you would have all three phases, solid, liquid, and a gas, in equilibrium for water. So and you can see you can see all of the shape of this has a certain shape. Other materials have different shapes for their phase within their phase diagrams. Here are two examples. Here's one for carbon dioxide. Here's one for sulfur. Now, phase diagrams can actually become kind of complicated. Here's what I'm going to do. I'm going to put these, move these aside and put this one next to it so that we have three different phase diagrams to compare. Water, this is CO2, and this is for sulfur. Okay, now the point being here is the real point I want to make is that different substances will have different sort of shapes to their phase diagram. In between water and CO2, the slope of this change in freezing point or melting point with pressure goes in different directions, right? In here it's got sort of a negative slope, and in this case it's got a positive slope. Okay, the overall other parts are somewhat similar in shape, right? Some substances can have rather complicated phase diagrams, Many substances do have rather complicated phase diagrams, where in this case, this substance has two different types of solid crystal structures that it can exist in under various pressures and temperatures. And this is the case for many substances. So there's two different solid phases that sulfur can exist under. A rhombic and a monoclinic shape. We don't have to worry about that too much. The point is that you can use these phase diagrams to sort of predict which maybe phase structure would be the one that would be present at a given condition. It would of course have two different triple points in that case too, where you have equilibrium between three different phases